So now we're going to continue with estimating a population mean by finding the sample size needed, because a lot of it is, how big does our sample size have to be, right? We always ask that, like, well, how big is big enough, right? And I told you, well, let the sample size be, at least 30, right? How big is good enough? Well, that doesn't mean if I tell you, oh, it just has to be at least 30, that doesn't mean you're going to get the results you wanted. A lot of researchers end up doing is saying, well, if I want to be like, here's my margin of error, right? Let's say I'm trying to find the average. And let's just say, like, I don't want to be um, more than 1% within confidence. Like, I don't want to be 98% confidence. I want to be 98% confidence. How will I get the probability of success to be so high that I for sure will only be within one margin of error, right? So again, here's the So how big does a sample have to be good enough that the probability of success is so high, right? And that's what we're saying. We're saying if I want to be within the certain margin of error where I have this lower bound and upper bound, then what would be my sample size? What is a good sample size? Right? And that's all this means. So the first thing we have to do is be able to know a few things. So we definitely have to know what we want our specific margin error to be, and the sample standard deviation and the z-score, right? So we'll go ahead and go back to the sample of the pennies, and then we'll go ahead and do this one. So remember that pennies gave us some raw data, and within the raw data, we saw that the box plot gave us a normal distribution. So there are a few things we already know. So the first thing we know is that the pennies come from approximately a normal distribution. And the second part that we know is what's given to us. So we know that the sample standard deviation is 0.02. We know that we want to be within 99% confidence, right? Okay, and so if we want to be within 99% confidence with a sample standard deviation of 0.02, notice that they want our margin of error, our MO, to be equal to 0.005 grams. Okay, so I think we're ready, and what we really want to do is try to find this sample size, like how big enough does it have to be so the probability of success is high enough that we can be within 0.005 grams of the population mean. So let me go ahead and draw what this looks like. So here's the middle, right? And there's the population mean, right? And then remember at the population mean, our z-score is 0. 99%, right, is this middle 99%. Let me shade, right? It's just confidence. And, well, I had to get the red. So here, 99% confident. So we had this before, remember, because there's 1% left over, which means there is 0.5% in each tail. Right. And so here are the lower bound and upper bound. We're not going to worry about that, but what we want to talk about is we have the z-score with respect to this area to the right. Remember that we said that this was z sub alpha, right? So this has to be z sub 0.005, right? Because 0.5% is 0.005. So just using symmetry and what we know about the normal curve, this means this z over here is going to be negative z sub 0.005, right? It's just the negative z-score because z is 0, to the left is negative, to the right is positive. So we're just looking here at the z-score level. Okay, so now we can continue to build what we need at this point. Okay, so recall that if alpha is our leftover percent, 1%, or in other words 0.01, that means alpha over 2 is equal to 0.5%, right, or 0.005, and therefore z sub alpha over 2 is equal to 0.005. And that's essentially what this number comes from. So what does that mean? That means that z sub alpha over 2, or in other words, z sub 0.005, is equal to the inv norm of area to, well, in this case to the left, 0.005, comma, and then the mean there in the middle is 0, and then the z-score in the middle is 0, and then we use standard deviation to be 1. And then we're going to do right, because that's the area to the right. So this is why we emphasize this z sub alpha, t sub alpha area in the tail, right? Because we knew we were going to need it now. So again, it's just really what it is just area in the right tail. However you want to look at it, like mathematically or by a picture, really all you're doing is finding a z-score for an area 0.005 in the right tail. That's it. You would put it in the calculator under inv norm. So you'll go to second vars and go to number 3 and just put 0.005, enter 0, 1 all the way, and then select right and then paste. So you have 2.576. Okay, so here are the pieces that we're going to need for our sample size. We're going to need S, E, and Z sub alpha over 2, right? So let's go ahead and do this quotient. So this means that, let's sample. Okay, so let's go ahead and find the sample size. The sample size is z sub alpha over 2 times the sample standard deviation over the margin of error squared. So I'm going to plug and chug. So 2.576 times 0.02 divided by 0.005, and then square it. So let's go ahead and put this in the calculator. I'll put a parenthesis, put 2.576 times 0.02 divided by 0.005, and then square it. So we get 106.172. See? So in the calculator, it becomes 106.172 ... right? But if this is pennies, right, we would assume that we're not going to have 0.172 of a penny. So you'll go ahead and approximate and round up to the nearest penny. So that's the numerical answer. There is a little preliminary work, but we did most of it. The only piece that we needed was the z sub alpha, and you can do that by inv norm. right? Right here, just get the area from the right and then go ahead and plug and chug. It's pretty simple. You just kind of have to know where to grab from. So what this means is that we would need a sample size of 107 pennies so that the population mean weight of pennies is within 0.005 grams with 99% confidence. That's kind of like the mental part that we should be thinking about. So what this says is we would need a sample size of 107 pennies so that the population mean weight is within 0.005 grams with 99% confidence.